You clicked because you know standard navigation is hitting a wall. Robots that map perfectly in empty rooms crash the moment a chair moves or a door closes. The real stake here is that geometry alone cannot guarantee long-term autonomy in the real world. By the end of this video, you will understand why adding a semantic memory layer is not just an upgrade, but the only path forward for reliable systems. For years, the robotics community has relied on the Robotics logistics case study as the gold standard for production-grade stability. It proved that the Nav2 framework could handle complex warehouse paths in simulated static settings with remarkable reliability. But that case study notably lacks semantic memory features. It works because the environment never changes. The moment you introduce dynamic elements, the brittleness of metric occupancy grids becomes a critical failure point. These grids treat every change in geometry as a total system reset, forcing the robot to replan from scratch whenever a transient obstacle appears. Here is the thing about standard Nav2 deployments. They rely solely on geometric cost maps to make decisions. This means the robot interprets the world as a collection of occupied and free spaces without understanding what those spaces actually are. If a robot sees a blocked aisle, it knows it is blocked, but it does not know why. It cannot distinguish between a temporary obstacle like a dropped box and a permanent change in the environment layout. This creates a fundamental disconnect between the robot's perception and its ability to act intelligently. The system treats a kitchen and a hallway as identical if the geometric footprint is the same, leading to navigation failures in environments where semantic intent remains constant even as geometry shifts. Recent implementations of vision language models within ROS2 are changing this paradigm. Frameworks integrating CLIP directly into the Nav2 behavior tree are providing the first concrete evidence that semantic layers are essential for dynamic autonomy. Instead of matching geometric features, these systems enable robots to interpret concepts like kitchen or blocked aisle. This allows the robot to navigate to the red door even when visual features are occluded or lighting conditions change. The localization process transforms from a geometric matching problem into a semantic concept retrieval task. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the implications of this shift. A robot equipped with this capability does not just see a wall of pixels. It understands that the area is a kitchen. It can recall that kitchens often contain cluttered counters, or that aisles might be blocked by delivery carts. This is where the concept of semantic memory becomes the differentiator. True long-term autonomy requires an architecture that persists beyond the current session. The robot must be able to recall high-level environmental states, such as the kitchen being cluttered, to predictively adjust navigation costs before geometric sensors even detect a collision. Without this semantic memory, robots fail to generalize across sessions in dynamic settings. They repeatedly relearn the same layout changes, wasting computational resources and time. Embedding semantic tags into the global cost map allows for one-shot adaptation to new environments, a capability that is entirely absent in pure SLAM approaches. This means that once the robot learns a semantic rule, it can apply it to future scenarios without needing to remap the entire physical space. However, we must be intellectually honest about the production trade-offs. Integrating vision. Language models introduces significant computational latency. The overhead of VLM inference is substantial compared to the lightweight real-time performance that Nav2 typically guarantees. Successful implementations must offload semantic reasoning to asynchronous background processes while maintaining real-time geometric safety via the existing local planner. If you block the main control loop with semantic reasoning, you lose the real-time responsiveness required for safe operation. The reliance on asymptotically optimal RRT planners for semantic pathfinding suggests that current algorithms may struggle with the computational overhead of real-time semantic reasoning in large-scale deployments. While the Robotics case study validated Nav2's reliability in static, simulated settings, it highlights a gap between current production-grade stability and the advanced autonomy required for complex, changing worlds. We are seeing the first concrete evidence that semantic layers are essential, but the hardware dependencies complicate the picture. Many of these advanced systems depend on specific hardware like Intel RealSense RGB-D cameras to function correctly. This complicates the deployment of lightweight, real-time performance Nav2. The system requires a specific sensor suite to capture the visual data that the vision language model needs to interpret the scene. This dependency creates a barrier to entry for teams that want to implement semantic navigation without investing in a full sensor upgrade. It forces a choice between the robustness of a generic geometric approach and the adaptability of a semantic one, often at the cost of computational resources. The path forward requires decoupling the semantic layer from the geometric layer. This separation allows the robot to use the fast, reliable geometric planner for immediate obstacle avoidance, while the slower semantic layer handles high-level planning and memory retrieval. This hybrid approach leverages the strengths of both systems. The geometric layer ensures safety and real-time performance, while the semantic layer provides the context needed for long-term adaptability. This is the only way to achieve reliable autonomy in environments where geometry alone is insufficient. We are moving beyond basic SLAM by adding a memory layer where semantic maps persist. This enables long-term adaptability without constant remapping. The shift is from a robot that reacts to what it sees right now to a robot that remembers what it learned yesterday. This is the critical evolution required for robots to operate effectively in the messy, unpredictable real world. The technology is there, the frameworks are available, but the engineering challenge is managing the latency and hardware dependencies to make it practical for industrial applications. The future of robotics lies in this integration. As vision language models become more efficient and hardware becomes more capable, the gap between simulated performance and real-world adaptability will close. Until then, engineers must navigate the trade-offs carefully, balancing the need for semantic understanding with the constraints of real-time computation. The goal is a system that is not just smart but resilient. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.